And then there were 4. So I'll begin with a word of prayer. Dear Father, we thank you again for this opportunity we have just to meet together and to study your creation. Thank you, Lord, for these students. Just pray to be with us today. Help us again, Lord, to glorify you, what we do, and just give the students understanding as they work on the math today. In your name I pray, Lord Jesus. Amen. All right. I had threatened to start convolution, but I shouldn't do convolution until I've done some of this Dirac Delta function stuff. And so let's talk about the Dirac Delta function. Dirac, one of the founders of quantum mechanics, interesting fellow, pretty good at math. He had a pretty good sense of like when things went too far. So he probably wouldn't pursue those things, but there'd be like a little comment in his physical writing like, this makes sense for such and such order, but not past quadratic or something. I mean, he's mathematically careful in his way. And this was one of the things that I think he popularized. I'm not sure of the exact history of it, but the reason I say function is not really a function. So like I told you guys last time, here's the sort of informal definition for it. Dirac delta function of t minus t naught is equal to, and this is just, it's infinity. T is equal to t naught, and it's 0 if t is not equal to t naught. This will get you into not too much trouble, but a probably more accurate definition, if you will, at this level of math anyway, is the following. It is this object such that if we integrate over some interval I some function f of t times the Dirac delta function of t minus t naught dt, well, we get just f of t naught. So provided t naught is an element of I. So like if you integrate over some interval that contains the time t naught, then the Dirac delta function, the slogan I like is that the Dirac delta function turns integration into evaluation. So Dirac delta functions are actually really, really easy to integrate, right? Now, so here's another, why. One motivation you could see it is just sort of from extending calculus. If we look at the unit step function, right? What's the graph of the unit step function look like? At t naught, well. So let's see here. So this would be the unit step function, right? And then like that, right? This is y equals to unit step function of t minus t naught. As we described last time, it's 0 if t is less than t naught. It's 1 if t is greater than t naught. We use this to build formulas for discontinuous functions, right? We learned how to take the Laplace transform of this last time. I guess I should say last week. Also known as yesterday. But yes, I hope you've done homework this last week. Anyway, so if you think about the derivative, what would du, what's the derivative with respect to time of the unit step function? Right? It's clearly 0 if t is not equal to t naught, right? Because if t is not equal to t naught, this is a constant function, right? But what happens at t naught? You got this jump, right? So all of a sudden, at t equals t naught, you've got this, spike. You go from there to there in no time, So if I was to graph the derivative, it'd basically be 0, right? 0, and then right here, it's like that, So this is delta of t minus t naught. equal to y. What is the, if you think about the definition above, which I'm about to box in green, if you look at that definition, what would the graph be for the integrand? Can you think about that? How would it differ from what I've drawn in red? What would the difference be? It would just be, you know, it's this, I'm basically just multiplying the height of the red spike by f of t, not. It's still infinite. I know. But anyway, so this is basically, if we had that, what happens if f of t is just identity, if it's just 1? Then this just reduces to the integral over I of the Dirac delta function t minus t naught equals to 1. So there's a unit area under the Dirac delta function at that single point. You know. Now, obviously, these things I'm telling you are mathematically heretical, right? I mean, these are not legitimate comments about the calculus of functions. That's why I put quotes. It's not actually a function. To technically and carefully understand this, you have to think about like sequences of functions which share some common trait. So, and also this is you know, also really, at least for things like switches, this isn't really the accurate model of a switch either, right? Like an actual physical switch, what's happening? You know, you have your T naught, and you have, say, you know, T naught plus delta T, and you've got T naught minus delta T, something like that. Or maybe we just keep it simple and say, you know, you've got some delta T band about T naught, at which, the middle tick is supposed to be T naught. I can't draw it in there. It made it too small. And about that, you know, the actual, like a physical switch is something more like this, right? It's 0. Then what happens? At like some initial time, you start going up, right? And then at that final time, then you're where your switch goes to, right? So this would be something more like an actual physical switch, right? It doesn't happen in an absolute instant. It's not like you're going from 0 to 1 just that fast. There's some finite increment of time which it takes for the switch to go from 0 to 1, right? And so, but if you look at that, right, the derivative of such a thing is 0, right? And then it's a spike. You know? And so I usually make it more spiky, but I ran out of board space. So I think that would be more like what an actual physical switch looks like, right? And actually it would be it might be really complicated how an actual physical switch works, right? Maybe an actual physical switch isn't linear like that. Maybe it's got some kind of, you know, noise and junk going on between the transition, right? And so correspondingly, the spike would actually be much more complicated. So what the Dirac delta function is doing is saying, I don't really know about that delta t. I don't really know about the shape of the transition. I just know that the big story is it starts at 0, it goes to 1, like that. So it's in some way way of encapsulating a certain amount of ignorance about the transition. That's one way you could look at it. Now, from a basic physics perspective, it really says that charge is localized if you use the delta function to build the charge density, like I told you guys last time. The application of this, three-dimensional. Three-dimensional application, which is worth talking about for a second here, is if you have the charge density as a function of x, y, z, then you could do q, Dirac delta function of x minus x naught, Dirac delta function of y minus y naught, Dirac delta function of z minus z naught. What this would do is, the way this would work is it basically says the integral of, you know, this charge density times dv over some volume, it's equal, it's case-wise defined. It's either q if x naught, y naught, z naught is in the volume, and it's 0 otherwise. So this is a formula for, you know, charge per unit volume in the case that you have a charge localized in space. And So Gauss's law in differential form, what's it say? You may or may not have learned this. If you've had I guess you guys probably haven't had fields and waves yet, right? I mean, you haven't had the electromagnetism course if you're an electrical engineer. Some of you never will. It's a prereq. Good, good, good. So, and unfortunately, I wish we had physics 2 as a prereq for that course, but whatever. Another story. Let's see here. The divergence of the electric field is the charge density divided by epsilon naught. This is the so-called differential form of Gauss's law. All right. So, what would be an example of a physical situation where you had this, isolated point charge? Well, it's the thing we teach in the second physics course, Physics 232, the so-called Coulomb field, just a single point charge at the point x naught, y naught, z naught. It's exactly involving this math. It's not some kind of highfalutin exotic example. It's the basic example requires the Dirac Delta function to say what the charge density is. And so, in Calculus 3, which you guys have had, you learned that if we integrate the triple integral over the volume, right, of the divergence of a vector field, right, what's it equal to? It's the very end of Calc 3. Guys remember? We can trade that for integral over the boundary of the volume, right? In other words, the surface integral of E, the flux of E. This is Gauss's theorem or the divergence theorem, or if you're Russian, it has another name. I don't remember. Sorry. I have respect for the Russians. I just am not very good at remembering their names. Ostrovigotsky or something. I don't know. Anyway, so these sorts of natural theorems are often discovered by different mathematical communities because they're logical consequences of the previous math that you've learned. Contrary to what the sociologists say, they are not consequences of society. There are people who say that the physics that we learn and find are consequences of the society in which they're found. I know. Yeah, exactly. It's crazy. The theorems that we find are a consequence of the objective reality which we're exploring with logical minds, which is why you find completely the same physical theories being found in completely separate political systems, shockingly. Anyway, sorry, I digress. I had a course as an undergraduate. It's still bothering me, the absurdity of what was said in there. Anyway, so I digress. This would actually be what? This is the integral over the volume of the charge density divided by epsilon naught, right? dV. And so if we're dealing with this point charge density, what does it give you back? It gives you, we just pull the 1 over epsilon naught out. What happens if the volume contains x naught? Let's suppose that this volume has the point x naught, y naught, z naught in there, right where the charge is. Right. Well, no, it should be, I kind of told you the answer here. We just have to take this and divide by epsilon. So just q over epsilon naught is the thing. And on the other side, we have, we usually use a big phi, the flux. Or if you like, the number of field lines, streamlines of the electric field which are flowing out of the volume. And that's the Gauss's law that you learn in Physics 232. But to connect the integral form of Gauss's law to the differential form of Gauss's law, it requires the use of Dirac Delta functions, or some kind of sneaky mathematical procedure, which I would be, well, anyway. There's another game you can play to get around using Dirac Delta functions. You can also assume that the point charge is over some like really tiny sphere smeared out in a continuous way and work around that. But if you ask me what's the size of an electron, as far as I know, we don't know. So, since we don't know, the Dirac Delta function is not a bad mathematical formulation for it. Anyway. enough about that. I just wanted to give you a little bit about what Dirac Delta functions are, what they're used for, before we just go do a bunch of problems. Okay. Now, let's get back to mechanics. What's the Dirac Delta function for in mechanics? So where's the Dirac Delta function? So think about this. The net force, right, is equal to dp dt, right? Or one-dimensional, drop the vectors, right? F is dp dt, right? So, you know, if we integrate from, say, t1 to t2 of f of, you know, as a function of time, let me just drop the of time. If we integrate the force over time, that is going to be the integral, right, of p1 to p2 of dp. In other words, it's p2 minus p1. It's the change in momentum. We have a name for this. What's this? It's a change in momentum over a time interval. Impulse, right. So one interesting force you can think about, and this is something we never really ask you questions about in Physics 231 because it's, well, maybe there's an instance of it. Like we do assign the problem where somebody throws a ball and then you hit it with a bat and you talk about the change in impulse, right, on the tennis ball as it hits a bat, or a baseball as it hits a bat, or a ball hits a wall and bounces off, something like that. This would be kind of like that. Another instance would be something like, you know, you got a nail, and then you take a hammer, right, and then. And so if you think about the force graph for a hammer hitting a nail, what's it look like? If it hits at time t naught. If you think about that, the force time graph of a hammer hitting a nail, it's something like 0, right? And then there's this big spike, and then, you know, 0 again, right? And so if this is a force time graph of the force of a hammer hitting a nail, then there's a significance to the area under that force time graph. What's the significance of it? It's the impulse. It's the change in momentum delivered to the nail, right? And so what would so if you want to write a force function, right, which gives you, say, an impulse of j naught delivered to a nail at time t naught, the formula for that would simply be this. I say f of t equals to, let's say, j naught, which is a fixed constant, right, and then delta of t minus t naught. So this is the force, the formula for a force which delivers an impulse of j naught to a nail at time t naught. And so that's also why we sometimes call the Dirac Delta function an impulse, a unit impulse. See, because it gives an impulse of 1 unit of momentum if we don't have the constant j naught, right? Ignoring the j naught, we have an impulse of 1. Okay, enough motivation. Let's talk about how to do some calculations with these. So, how to calculate. So first order of business, what's the Laplace transform of, delta of t minus t naught? Integral from 0 to infinity, right? Delta of t minus t naught e to the what? Minus s t naught dt, right? Did I put a t naught in the exponential? Good grief. No, that's not there. Remember the definition. So all I'm doing is taking the definition of the Laplace transform and putting delta function in place of f. And so again, what's the delta function do? It turns integration into evaluation. So this is just what? E to the minus what? E to the minus s t naught. example 1, if we had the Laplace transform of J naught delta of t, J naught's a constant, it still pulls out, and so we have the Laplace transform of delta of t. What's the Laplace transform of the Dirac delta function? With, if t naught's equal to 0, we have e to the what? E to the 0, which is just let me get my example count up here. Example 2, Laplace transform of delta of t minus 2 minus 3 Dirac delta function of t minus 7. Ooh, there we go. So the first one produces a e to the minus 2s. And the second one produces minus 3 e to the minus 7s. It's kind of a funny thing, but it's easier to solve problems where the forcing function is a Dirac delta function or some combination of them, as opposed to unit step functions. Yesterday, I did one where we had a second order differential equation equal to a unit step function. That resulted in us having to do partial fractions on a cubic denominator. It wasn't too bad, right? We did about 10 minutes to end of class, but you know, it turns out, as weird as this stuff is, it's actually easier to do these problems. Given a choice between solving a forcing function being a delta function or a unit step function, I would choose the Dirac delta function in an instant. Much easier problem. So let's look at an actual differential equation with this, right? I once had a course when I was undergrad. It was my junior level electricity and magnetism course. And I had a Chinese professor, Dr. I think it was Chang, and he had the ability to like write at the very bottom of the board. He would take this stance, which was like Frogger. Like one leg would go this way, one leg would go that way, and they would be like, his knees would be like right angles. It was an amazing stance. I could not replicate it. It was amazing. But I very much remember him asking us what the derivative of the unit step function was. And we stared at him blankly. Like, you can't differentiate it, it's discontinuous. Because we were also taking like math courses at the time where it had been drilled into us. You can't differentiate discontinuous functions, right? And then my physics professor is asking me, how do you differentiate a discontinuous function? Very, very troubling. And then the fact that we couldn't produce that it was the Dirac delta function like I just erased here. And then he laughed at us for not knowing this. And I was like, so mean. It's the difference in cultures, I guess. Physics and math. Anyway, I digress. Here's an example 3. Let's see if we can solve. I'll keep it simple to start with. Y prime prime plus y equals to 3 delta of t minus 1 plus 2 delta of t minus 4. There we go. And to keep things simple, we'll suppose that y of 0 is equal to y prime of 0 is equal to 0. Sometimes it's nice to do an example like that. So let's do one of those. So first order business, we take the Laplace transform of both sides. What's the Laplace transform of y prime prime? Well, it's s squared big Y. And then the Laplace transform of little y is big Y. And that would be 3 e to the minus s plus 2 e to the minus 4s. So I took Laplace transform of star. All right. Next order of business, solve for big Y. So this is really what? This is really s squared plus 1 times big Y, right? So solving for big Y, I get y, big Y rather, is equal to 3 over s squared plus 1 e to the minus s plus 2 over s squared plus 1 e to the minus 4s. Let me invent some labels, all right? I know society has taught us not to label things, but they're wrong. Let's see here. F. Labels are healthy. They're useful. Sorry. I don't know. Are we really against labels? I'm not sure. Anyway, so if this is big F and that's big G, what's the inverse transform? What's the inverse transform of this? What's the inverse transform of that? In other words, what's little f of t and what's little g of t equal to? I'll do the first one. 3 sine t. You do the second one. What do you guys got for me? Okay. I'm sorry, that was condescending. After I answered the first one, it's not healthy for me to ask the second one. I apologize. That was not nice. Let's see here. I mean, this is an insulting question. I shouldn't ask it. Let's see here. Y, little y then, of t, is equal to, now I'm going back to a theorem, which is that the inverse Laplace transform, let's see here, and I'll use of f of s times e to the minus as, just to, well, this is equal to little f of t minus a times u of t minus a. So if we have exponentials in the s domain times functions, when we take the inverse transform, we shift the time argument and multiply by the appropriate unit step function. So this would be 3 times the sine of what? Not t, but t what? Yeah, t minus 1. And that's u of t minus 1. And then over here, plus 2 sine of, I won't ask you guys how to do this again. The whole issue of being polite. T minus 4. Now, I mean, you could reformulate this and figure out, it's possible, all right, guys, it's possible to rewrite this in the form a, well, first of all, 0 for t less than 1, right? And then it would be a sine of t, a1 sine of t plus v1 for 1 less than t less than 4, and then it would be like a2 sine of t plus v2 for t greater than 4. There's some phase angle that you could find to rewrite it as an amplitude times a sine starting at some particular phase angle. You could find constants a1 and a2 and phi1 and phi2 to make it so. Basically, this is a spring without friction, and you're hitting it with a hammer 2 times. One giving it an impulse of 3, the other time giving it an impulse of 2. And this is the motion that results. It just sits there motionless until you hit it with a hammer. Whack. Vibrates, you know, according to A1 amplitude. And then at time 4, you hit it again, give it 2 units of impulse, and yeah. So a fun question to ask would be like, if at time 5 you want to hit the spring with a hammer such that it stops, you know, Is it possible? Do you have to hit the hammer? I mean, I guess you could think about hitting the spring either coming or going, right? Actually, I think if you actually think, so the displacement of the spring is positive, right, if it's extended. So if you think, I mean, I think if you think about, these are kind of difficult. If you start thinking more about it physically, it's kind of tough to come up with hammer hits like that, right? Because if this is y greater than 0, like when the spring is extended, that's when y is positive, right? So if I put positive forces over there, that would be, if I'd have to somehow hit the backside of the spring, like whack, to produce those forces, right? To actually produce forces that went this way, I would need minuses, given the sign conventions of the spring force. But anyway, do you guys want me to show you how to find A1 and Phi1? Do you know how? Let's talk about how to do that, at least let's find the A1 and Phi1. That's a good exercise. It's something that we should be able to do, but I do think that if I was to take a survey, probably only about 5% of the students taking this course could do that without, having a homework problem and some other stuff leading up to it. Maybe if you really thought about it, if somebody made it worth some money to you, you could do it. You're like, a few minutes on Google, I'd have it. It's probably true. So let's see here. So what we're trying to do is rewrite 3 times the sine of t minus 1 as equal to A1 sine of t plus some Phi1. In other words, our goal, find A1 and Phi1 to make it so, to achieve that. All right. So, what we could do is that would be 3 times the sine of t times the cosine of 1, right? Minus 3 times the sine of 1 cosine of t. And then on the other side, what we would have is A1 sine t cosine Phi1 plus A1 sine Phi1 cosine t. You already know that the answer is not entirely unique, because if Phi1 works, we could also add 2 pi to it, right? Or we could subtract 2 pi from it. Where you start the trig functions kind of, but maybe we should limit Phi1 to be, less than 2 pi in magnitude or something, or less than pi in magnitude. Anyways, we're looking for a solution, not all solutions. So let me set my sights a little bit lower. If you look at this, we need 2 things, right? If we look at the cosine terms on both sides, we need those to match up, all right? And if we look at the sine terms on both sides, we need those to match up. The logic for that is that the set of functions sine t, cosine t, if you take the Wronskian of them, you get non-zero. In fact, these are linearly independent functions on the whole real line. And the thing about linearly independent functions is they behave just like polynomials. So like if I have 2 polynomials equal, I can equate their coefficients, right? Sine and cosine are like that. If I have an equation for all time in sines and cosines, I can equate the coefficients of matching sines and cosines. So this actually gives me 2 equations. It gives me 3 times the cosine of 1 is, what is it? Lost track. Oh yeah, A1 cosine Phi1. And I also get that minus 3 times the sine of 1 is, what is it? It's A2. I'm sorry, it's still A1. A1 sine of Phi1, right? All right, 2 equations, 2 unknowns. That's better. They are nonlinear. It's kind of a drag. Can you think of how to eliminate A1? Yeah, we could do that. So you're like, solve the second one for a1 equal to minus 3 sine of 1 over sine of phi 1. And then plug that into the 3 cosine of 1 is equal to minus 3 the sine of 1 over the sine of phi 1 times the cosine of phi 1, which implies that, we got here, implies that the tangent of phi 1 is equal to minus 1. So now that we've just, like, your algebra was good, but another way you can look at that is just to divide the second equation by the first. Right? If I divide this by that, and if I divide that by that, then I get, oh, yeah, I'm sorry, tangent of 1. I actually need to think through the algebra. You guys shouldn't agree with me. Sorry about that. Yeah, there's a sine and a cosine in there. So if I divide the cosine 1 over there, I get a minus tangent 1. And if I bring the sine phi 1 and the cosine phi 1 on the other side, I get the tangent phi 1. But my point is, we could also see that final equation from just dividing the equations. But there you go. I mean, so phi 1, we can choose phi 1 equal to the inverse tangent of minus the tangent of 1. Is inverse tangent an odd function? What's an odd function? We can pull minuses out of odd functions, right? What's the graph of inverse tangent look like? It's this tangent on its side, right? It's this. It's got it's got horizontal asymptotes rather, where vertical asymptotes were in the tangent, pi over 2 and minus pi over 2. In fact, yes, the inverse tangent is an odd function, which means I can pull that minus out, and I get inverse tangent of 1. Well, that is just minus 1. Okay, so phi 1 equals minus 1, great. Now how do we find a1? Let me suggest to you that we square both equations. Square both equations. I mean, well, by the way, so is it clear to you that we can take a1 to be positive before I do that? Looking at the blue equations, you can see we can take a1 to be positive because we just chose phi 1 to be minus 1. If phi 1's minus 1, that pulls a minus out here, and we'll get minus 3 times sine. Oh, maybe I should just do that. I'm an idiot. Just plug. I'm making this too hard. Now we found phi 1. Plug it into either one of these equations. We got it, right? Duh. Okay, I'm an idiot. Let's see here. So, like, which one do you got? I mean, here. 3 times the cosine of 1 is equal to a1 times the cosine of minus 1. Cosine minus 1 is just, these are both 1. And so, therefore, a1 is the, 3, right? 3. So what we just worked out is that between time 1 and time 4, we actually have 3 sine of I'm an idiot. I am such an idiot. Why'd you guys let me do this? You guys, why did you let me do this? This was obvious from the start. A equals to, A1 is 3, and phi is minus 1. Yeah, okay. Good job. All right, I now have to do the next case. Otherwise, I mean, let's find A2 and phi 2 then. That should be slightly more exciting. Goodness gracious. That is what we call being too close to the board. Hey, you guys didn't stop me. It's on you too. Example. I think this deserves a new number. This is example 4, aka example 3, continued. So what we want now, when t is greater than 4, what we have is y equals to 3 sine of, is this going to be boring too? No, 3 sine of t minus 1 plus 2 times the sine of t minus 4, right? They're both activated. They're both. So in other words, you hit the spring with a hammer at time 4. It doesn't undo the fact that it was hit with a hammer at time 1. The influence of hitting the spring with a hammer at time 1 continues on. All right, and that was a 4. Go. Maybe I should just stop for today. All right. I don't know. There's different games I could play here. Let's just be boring. So this is 3 sine t cosine 1 minus 3 sine 1 cosine t. Let's see here, plus, what is it, 2 sine t cosine 4 minus 8, oh, I'm sorry, not 8, minus 2 sine 4 cosine t. So put it all together, I've got sine t, 3 times the cosine of 1 plus 2 times the cosine of 4. And my cosine t terms are minus 3 times the sine of 1 minus 2 times the sine of 4. So we'd like to say that that's equal to, a2 sine of t plus phi 2. What's that make the a2 and phi 2 have to be? Well, again, this is going to be a2 cosine of phi 2 times the sine of t plus a2 sine of phi 2 times the cosine of t. And again, we have to have bilinear independence of sine and cosine. We have to have that this business right here matches this guy. And we have to have that this here matches that. So I suggest we've got a2 sine phi 2 equal to minus 3 sine of 1 minus 2 times the sine of 4. And we've got a2 the cosine of phi 2 is equal to 3 cosine of 1. Wait a minute. Oh yeah, I'm sorry. It's bothering me all of a sudden that there was cosines in both and sines in both, but of course there is. Idiot. All right, 3 cosine 1 plus 2 cosine 4. Oh, fine. So to eliminate a2, which is clearly non-zero here, all we got to do is divide the equations, So dividing equations gives me that the tangent of phi 2 is, minus 3 sine 1 minus 2 sine 4 divided by 3 cosine of 1 plus 2 cosine of 4. And then you take the inverse tangent of both sides, and that gives you a choice for phi 2, right? Which we could get our calculator out and find a specific numerical value for if we were so inclined. There we go. And then what should A2 be here? I mean, technically, yeah, you could take that and plug it back into either one of the blue equations, you know, I suppose. Might be helpful to draw a triangle to illustrate what the phi2 means, right? I mean, you could do that. That might be helpful, although dangerous because the sign here is a minus. I think. I mean, sine of 4 is what? Is that negative? I think that's negative. Is it negative? Yeah, it's negative. Sine of pi is 0, and then past pi, sine gets negative. Oh, but there's that 3 there. I don't know. So how do you find A2? Well, one thing you could do here, and let me, if you don't mind, I'm going to be a little bit more generic. Suppose that we had suppose we had A sine phi equals to, say, x, and A cosine phi equals to y, like that. Just the generic algebra. What you could do is square both sides. So we get A squared sine squared phi equal to x squared, and A squared cosine squared phi equal to y squared. What happens when you add these equations? When you add those equations, you get sine squared plus cosine squared on the left-hand side, which is 1, and it gives you an equation for A squared, namely that A squared is equal to x squared plus y squared. So if you can see from some other argument that A should be positive, I'd actually have to get my calculator out. I don't know. I'm not sure without doing further numerical work if I've got the right sign choice here, guys. But certainly we could do A2 as either plus or minus. And we really should choose a plus or minus 3 sine of 1 plus 2 sine of 4 squared. I mean, I should just choose the plus and keep it positive. 50% chance I'm wrong, but, you know, whatever. So there you go. There's a larger point here. If you have any linear combination, right? This is a theorem of trigonometry. Theorem, if we have a sum, you know, I equals 1 to n of like a sub I sine of, you know, omega t plus phi I, right? Then that is equal to a sine of omega t plus phi for appropriate choice of amplitude and phase. What I'm saying, this mathematical theorem I'm stating corresponds to the fact physically, if you superpose waves of the same frequency, the net result of that is a wave with the same frequency. So this is, you know, you find constructive and destructive interference happening inside this theorem, you know. For example, if you add this wave to this one, right, we get this wave. On the other hand, if you have, you know, twice the same thing, you get a wave of twice the amplitude. But then there are other, when they don't quite match up, you might think that you get something other than a wave of that frequency, but no. Trigonometry says you get back a wave of the same frequency if you add waves of the same frequency. Now, if you add waves of different frequencies, then you get more interesting things like beats, right? And other things, but sorry, I got a little bit off track here, but I think it's a good thing for you guys, because one of the things I would like for you to leave this course with is some, at least, you know, a better understanding of how to work with formulas involving trig functions. Now, there is a better way to do this in terms of what are called phasors, right? but you guys will learn that in your engineering class. So I'm not going to get into it too much in here, but if you look at things as being part of an imaginary exponential, like the real part of an imaginary exponential or the imaginary part of an imaginary exponential, you can replace these calculations with appropriate calculations in the complex plane, which once you get used to the bridge between the world of real and complex math, that's faster. If you look at the Wikipedia article on phasors, it's got a very decent introduction to this with even with like a little animation showing you the phasor and the wave that results. It's very neat. So I don't know. I don't know why I don't hear people badmouth Wikipedia much anymore, but there was a time when it was just not appreciated. Anyway, I mean, I'd trust Wikipedia before I'd trust a printed encyclopedia. Printed encyclopedia has what? Maybe a dozen editors, maybe a couple experts. Wikipedia, you find a popular article on something that's important to nerds, you'll have, like, who knows how many people arguing over what should be there. There's actually a pretty good chance you're going to get a more complete exposure to a topic using Wikipedia than an old-fashioned encyclopedia. Anyway. And it's gotten harder to edit Wikipedia, so like the likelihood you're going to find fake stuff put into the middle of an article is somewhat slim. But all right, so let's look at another example. Where was I? Example 5. Thank you. Let's try to solve y prime prime plus 4y prime plus 4y equal to u of t minus pi plus delta of t plus minus 2 pi. There we go. And because the break is almost upon us, we'll again suppose that y of 0 is equal to y prime of 0 is equal to 0. Don't worry, I'll get back to making life less simple after break. Although we're almost done with Laplace transforms at this point, guys. There's really only one other little topic I need to talk about, so I'll try to get to it. There are a fair number of things in the chapter, by the way, which I don't really spend class time on, and maybe that's bad. For example, the gamma function is worth reading about, and maybe I'll talk about that for a minute after class. Not after class, but after the break. And trying to think what else it is that I've left out. I will not cover periodic functions. At the moment, I don't have anything to say about them. It's a hard topic. I would really need to spend like a whole class to really get into it. I haven't found good homework problems for it yet. I figure that you'll learn about Laplace transform of periodic functions when you need to use it in your engineering class. So I try to focus more on the basic stuff in here for Laplace transforms and not. There is much more beyond what I've said. All right, anyway, what's the Laplace transform of this? It's 1 over s e to the minus pi s. We learned that yesterday. And then this guy gives me e to the minus 2 pi s. Then I solve for big Y. By the way, the coefficient here, what is this? Right? It's s plus 2 quantity squared times big Y. So this gives me 1 over s times s plus 2 quantity squared e to the minus pi s plus 1 over s plus 2 quantity squared times e to the minus 2 pi s. All right. Well, one of these Well, I mean, so there's, let's see here. So we need to do some work on this, right? I'll do the work over here to the side in just a second. So we can do partial fractions on that. 1 over s times s plus 2 squared should be a over s plus b over s plus 2 plus c over s plus 2 quantity squared. That's the partial fractions decomposition that we should be looking for here. So we can multiply both sides by the denominator. We get 1 is a times s plus 2 squared plus bs times s plus 2 plus cs. Here's a trick. When you have a repeated root, sometimes it's helpful to differentiate the equation. So this will give me 0 is 2a times s plus 2 plus b times s plus 2 plus s plus c. So let me call this star. Let me call this star star. It's just another thing you can do. It may or may not be helpful to differentiate the equation, you know? Now, I'll take star, and I suggest we set s equal to minus 2. I'll take star, and I suggest we set s equal to 0. Those should give me some really nice equations. S equals to minus 2 reveals what? 1 equals 2. Minus 2c, right? S equal to 0 reveals 1 equals 2. That's gone, that's gone. That's 4a, all right? Now, if we take star star, all right, and we put s equals to minus 2, we also get a nice result. We get 0 is equal to what? So this piece is gone. And let's see here, s equals to minus 2 gives me minus 2b plus c. Well, there we go. So apparently b is equal to c over 2. Now c is minus 1/2, and a is 1/4. And so c is minus 1/4. I mean, b is rather minus 1/4. All right, so we've got 1 over 4s. What was b? Minus 1 over 4 times s plus 2. Minus 1 over 2 times s plus 2 squared. So let me give this thing the name f of s. Oh, pick up pace. All right, inverse. I guess I'm gonna have. There's gonna be a little snippet. It's gonna happen. I happened yesterday too. I had like 30 seconds over the first hour. I was like, dang it. It's okay. The internet will forgive me, or the people who are not here. Hey, let's see, inverse transform of this, f of t is 1/4 minus 1 over 4 e to the minus 2t minus 1 over 2 t e to the minus 2t. And this other guy over here, if I call that g, then